Okay, so we will continue with Paavo Salminen. Will talk to us about optimal stopping of diffusion spiders.
I thank the organizers for the invitation. It's very nice to be in Toronto. And I found the weather to be almost like in Finland, but I believe that Toronto is anyway much southern than Finland. So I guess same level as Paris, perhaps. So I will talk today about diffusion spiders and their stopping. And I must apologize, this is the first typo on my slide, so it is not the 13th of May. Today it's the 12th, as you all know. So I hope there are not so many other typos. So, okay, what I present is a joint work with Jukka Lempa from Finland also, and Ernesto Mordecki from Uruguay. And this work was done some years ago, and there is already a ready paper. So I don't go much further than in this paper. In fact, I don't, for instance, take so many examples as there are in paper, but I also extend a little bit the framework. So this is the outline, and so first I introduce what is a diffusion spider. Sometimes it's also called diffusion on the spider graph or the spider diffusion. So it a little bit depends on the authors. So we choose this diffusion spider because you can see it's a little bit shorter than diffusion on a spider graph. So that's why perhaps we use the word diffusion spider. So the basic tool in this is a new formula for the resolvent kernel. And the resolvent kernel will be the main tool. And we see that this processes behaves in many respects as ordinary linear diffusions. Also, the structure of the resolvent kernel or the density, as I will show, has a similar structure. And then we discuss what is how we can analyze the excessive functions using resolvent kernel, and then use this theory and the classical theory of optimal stopping of Markov processes to introduce some verification, a new verification theorem for the optimal stopping value function for the optimal stopping of a diffusion spider. And then I also present some examples. So in this slide, I introduce the graph. It's denoted with capital gamma, and it has one node. Okay, so where is this up? So I don't get the, it's not the pointer.
You can press it at the top here.
Ah, I press it already. Oh. Okay, so it is this. So this is the graph. It has one node and then n edges. They all start from the node and goes to infinity. And this critical point is denoted with boldface 0. And this, okay, here are the points on the edges, arbitrary points, xi, I is the edge, x is the distance from this to the origin, this point 0. And then all these points 0, I identified with this node point. And the diffusion that we have the, so to say, start with, we can take a recurrent diffusion, which is living on R+. All these edges are parameterized on R+. And we take this to be reflecting at 0. And we assume that then 0 is so-called regular point. And the plus infinity at the other end is, we assume it to be natural. So I could very well use other kind of diffusions, but perhaps it's good to fix ideas that the diffusion comes back to the node point with probability 1. So to introduce the diffusion spider, so we use the notation boldface x. So here we have the diffusion at time t, and then this other component gives us the ray or edge on which the diffusion is. So we have one basic diffusion, and then we, so to say, split it to these different rays with some probabilities. So we say here that on each edge, the process before hitting 0 behaves like this given diffusion x. And then there are these probabilities, so to say, which determine, in a sense, which leg the process is. So we can intuitively think so that the process, when it hits 0, it chooses next leg with probability p1. But because the excursions accumulate at this point, we cannot say what is the next excursion. So this is only some kind of the intuitive idea. But this is the main problem, or the fancy, interesting thing in this process, that we cannot really say what is the next excursion. And the theory of this started perhaps with a paper by John Walsh, 78. And he called this process skew. He extended so-called notion of skew Brownian motion in this way, but he was considering even more general processes where the motion can choose any direction on a circle. And this is usually this process called the Walsh-Brownian motion. And then we have this, perhaps the Brownian spider is the one where we have a number of edges is n, so to say. So then the story goes so that the existence of this process as a continuous strong Markov process was proved in several authors. Rogers was using resolvents, Salisbury excursions, and then there's a semigroup analysis by Barlow, Pittman, and Yor. And but in these papers, at least, I couldn't find the resolvent density. So it is not given this there. And so to show you what is the resolvent density, so we do some notation. So we have the diffusion. It has a speed measure. It has a scale function, as in the book by Ito McKean. And so what? Because I'm using only one diffusion, so then in a sense my spider is homogeneous. But there is no restriction here, really. It changes a little bit the formulas, but I could use on any leg different diffusions also. I could also use transient diffusions. I could use very general setting. And so these were the probabilities. So I introduced the speed measure of the spider. In every leg, we have a measure. And so this is for convenience, so that we don't put any mass at the origin. And then similarly for the scale. So you see then that because the generator is given, so in the Ito McKean setting, so we have a generator is DDM, DS. So you see that if we are on the one leg, then these probabilities, so to say, disappear, and we have the generator of this diffusion on this one leg. And usual definition of the resolvent kernel is here. So we take the this refers to the expectation of the diffusion spider. And this is then the usual definition of the resolvent kernel of a Markov process. And integration is, this is a bounded measurable function. And another important one-dimensional linear diffusion in this setting is the diffusion, which I denote with x dou, partial or what it is. It has the same speed and scale as this x, and x has the 0 as the reflecting boundary, but this x has a 0 as a killing boundary. So in fact, this process is more important in the calculations than the original process. But to have this original process to be reflecting Brownian motion, it allows us to have a spider with only one leg, because then it is well defined also. Spider with two legs, and if x is reflecting Brownian motion, it's a skew Brownian motion. If I put there some other diffusion, then I get, with the two legs, I get some skew diffusion at 0. So now here we have the definition of the stopping time at 0 for the spider. And then we can use, because we accept here that the spider is a strong Markov process, we can write the resolvent kernel as the sum of the resolvent kernel if we have not hit 0 before. Okay, this is, so it is really defined here. So we take the Laplace transform of this expectation of probability, where we consider the spider before hitting the node. And this can then be expressed in terms of this basic diffusion, which is killed at 0, because we have the homogeneous case, and we have we denote this. This is the resolvent kernel for this killed diffusion. And so you see from this formula that I know this one, because this is a usual diffusion theory. This is a resolvent of the linear diffusion killed. And this we know also because this is the first hitting time of this diffusion at 0. So the only unknown thing in this is this one. Then we could find the resolvent kernel for the spider. And the question is now that how do we calculate this one? And I don't go into the calculations, but I say something after this theorem. So this gives us the resolvent density. And these functions are associated with the killed diffusion. And then if x is less than y on this leg I, then we have the density is the product of these two functions. If y is less than x, then it's other way around. And if they are on the different leg, then we have this kind of expression. And this resembles the resolvent density of a usual linear diffusion, where we have a decreasing function in here and an increasing function here. Of course, if we have a diffusion spider with some number of legs, and so perhaps we are here and we want to find the density of the resolvent between these 2 points, then of course we could put together all these legs which are not of interest. But still we don't have we cannot, what I'm trying to say is that we cannot reduce this problem to find the resolvent density to a problem of finding a resolvent density of a skew Brownian motion, for it's a skew diffusion. And so how this is then done? So we use excursion theory, and according to excursion theory, we can describe a Poisson random measure on the local time axis, and to find, and then because Poisson random measure that this disjoint sets are independent, we can argue from here, from this, that that the characteristic measure of the diffusion spider is a sum of the characteristic measures of the excursions of this diffusion. And then we have to we use then the theorem that this quantity can be expressed as an Laplace transform of so-called excursion law of an excursions, normalized. And this excursion law, so to say, it is expressed as the, so we can go FTA. So this is the excursion law of the excursion is in a set A. And when we take the Laplace transform, then we can say that this is F0 x, excuse me, m dx, when this is the density. So this is T, excuse me. And this is the density of the first heating time of the diffusion starting from X. H0 is in dt. And taking here Laplace transform with respect to T, we get the Laplace transform of the excursion entrance law. And this quantity gives us this, we have then GR F0 is equal to, okay, so it's better that I look at in my notes. Sorry. So this is the Laplace transform R1. So, and this this will be for the, so this is the sum pi p mu rf. So this reflects the fact that in the Poisson random measure, the disjoint sets are independent. These are the excursion laws for the diffusion, and integrating, we get we can integrate this explicitly, and we get the resolvent kernel. So, oops. Okay, and in the optimal stopping, it's good to understand the structure of the excessive functions of the strong Markov process. And the general form for the excessive function is can be written, expressed like this. So here, this sigma is a probability measure on the leg K. And here we have it is probability measure on the whole gamma, so that it can have a mass at 0, and then we have the coefficient is like this. So this is here. So in this, I have not, it is also possible that the measure put mass at the plus infinity at the endpoints. But for our purpose, it is enough to have excessive functions when the mass is concentrated on the finite part of the graph. So this is what this is I'm getting some parts of the Martin boundary theory. It says that there is a one-to-one correspondence between the probability measures on the compactification of the gamma and all Rx functions. And so what we will see now is the exact form how this singularity comes into these formulas. Because of course, the interesting point is what happens at the zero. We know probabilistically what there happens, but how does it take form in the formulas? And so if we have an excessive function, so then we can prove that right and left derivatives with respect to scale exist, and then this quantity gives the representing measure at zero, and this quantity is always negative because this is a measure and this is positive, so this is negative. So for excessive function, this quantity is always negative, which is an important thing. And we see then that other way around, if we have an excessive function, we can find the representing measure by calculating this quantity. We can find the representing measure at one point by calculating this quantity. And so you see here that because this is a measure, this difference must be positive. So it means that the left derivative is always bigger than the right derivative. And if it is differentiable, then there is no representing mass at this point. And again, the mass representing mass at zero can be expressed like that. So now I will show how this can be used in the optimal stopping. So this is something that one can assume that everybody is well acquainted here. So this says that the value is the smallest excessive R-excessive majorand, and the stopping set is where the value equals the payoff. So my payoff is denoted with pi. I assume here that it is continuous, but one can do other things also. And this is our verification theorem, which gives us information of the value function. So we assume here that that we can find a measurable function f such that this integral is finite, and then that the reward function can be written in this form. So this is something that we call the inverse formula. So we can think so that because this is resolvent, then this, so to say, we would like this to be the function that we obtain when we use the infinitesimal operator on pi, because then we get pi back. And so this, and then there comes this singularity term. I will show you how we calculate this in particular case. Okay, and so we assume now that we can find a Borel set such that if point is in Borel set, then the function is non-negative. And then if this value is less than 0, then this node should be in the, so to say, in the continuation set. O will be the stopping set and complement is the continuation set. And if this is negative, so it reflects that the 0, the function cannot, excessive function, for excessive function, this should be positive. So, and then we introduce this function v tilde. So you see that it is similar as this reward function, payoff function, but here we integrate over the set where this is certainly positive. This is the candidate for the stopping set. And then we have this additional term which reflects the singularity at 0. And so if this function is non-negative, bigger than pi, it is automatically non-negative because all these terms are non-negative. And if it is equal to pi on every boundary point on O, then this O is the optimal stopping set. And this is the optimal stopping time, and the value is equal to this v tilde. So this is based on the proof is based on the classical result that if we can find the function A and the function when you take the, you stop when you exit the Borel set A, this pi, if it is R excessive, expectation R excessive, then this value, this function, if it is R excessive and dominates the pi, then it is the value. So we prove this theorem in using this classical result. And so this condition, when they are equal, it gives us this equation from which we can perhaps choose find the stopping set. Of course, in generality, we should know something about this stopping set. Otherwise, for instance, we should have it good parameterized set. And so we can modify the proof of Koran from 2005 to prove that under some conditions there is a unique solution. The modification was done in our paper on the optimal stopping of multidimensional diffusions by Søren Christensen. And in this setting, so we assume that we have a, okay, so that we have these functions that we find in this verification theorem, and then every element has, so to say, those properties. And then there are these, it roughly says that we have an increasing sequence of sets. It says more, but also something about boundaries. So, but I don't go to that. And then we know that this equation has a unique solution. And for Brownian motion, this is an example. So we find all these functions for Brownian motion. We have the green kernel and then resolvent kernel, and we have this is the value, the reward, excuse me. We calculate, we notice that it has the representation with delta 0, and f function is like this. And then we can argue from the general theory many things about the value, in particular the smooth fit holds. We have a smooth fit theorem for spiders. And then we know that this value function has this representation, and we have the equation. And we prove that we can use as the family of sets this kind of the set. We parameterize with the points on the legs. And then we can prove that there is a unique solution in this family. And our equation, if we take 3 legs and some other quantities, then we can write the equation system like that, and we can find a solution. There's a unique solution, and this is the stopping points. And there are some references, and in our paper, so yeah, I can also say that it comes very close to this old results in this paper, but another setting. And in the paper, there are other examples, so, but now my time is out, and so thank you for your attention.